We're going to talk today about things that we know about the incenter of a triangle. So the incenter is made from the angle bisectors in a triangle. And so what that means is that each angle is divided into two congruent parts. The other thing that we need to know about the angle bisector, or about the incenter, excuse me, is that it is the center of the circle inside the triangle. And what that looks like is, for this triangle right here, it would be the circle that's contained inside of the triangle, and it touches each side of our triangle. And that's the only place that we can put that circle so that each side of the triangle is touched. So the center of that circle is the incenter of the triangle. And from this picture, we can see that if we connect our incenter to these points where our circle touched our sides, that each of those is a radii, or each of those is a radius. So that means that each of those segments is congruent. So we are equidistant from the sides of our triangle. All right. Something else that we may want to think about when we are making the incenter is we do know that each of these angles will be bisected. And also, since the circle has to be inside the triangle, the incenter will always be inside the triangle. It can never be outside the triangle. Okay, and that's really the only big characteristics of our incenter. So if we move on, we can do a couple of problems with this. So we move on to our next page, keeping in mind that our angles are bisected and that we're equidistant from all of the sides. And so looking at this picture, there's a couple of things that we need to consider here, and let's say that I said that that's z. And we need to find the measures of x, y, and z. So we start by looking at x, because that's just our natural first thing to look for, is the first variable, which would be x. And we have two pieces here that are sitting on congruent angles, because if this is the incenter, then what that means is that the segment connecting us back to this vertex was an angle bisector. So we split this angle into two congruent parts. So we have 2x plus 3. That's going to be equal to 4x minus 5. And so if we try and solve this for x, we can add 5 and also subtract 2. And we'll get that 2x is 8, so x is 4. Okay, and we've got x now. So we've solved for x. We are a third of the way there. So we move on to our next variable. And our next variable would be y. And y, as we can see, is an angle at the top of our triangle. And we have another one just like it on the other side. So that's another y. Down here, we have a 24. And right next to it, we're going to have another angle that's also congruent to that, 24. And over here, we didn't put the measures in here, but we could. If we plug in our 4, so we say 2 times 4, which is 8, plus 3, we get 11 degrees for each of those. And we could just double check with 16 minus 5, that's also 11. So our job is to figure out what the value of y is. And to do that, the easiest thing that we can do is look at our whole triangle. So excluding the lines inside of the triangle, if we just look at the yellow highlighted triangle here, we can see that this triangle should have 180 degrees total. If we total the measures of all of our angles, we should get 180 degrees. So together, I'll just redraw a smaller triangle down here just like it. At the bottom, we have 24 times 2, so that's going to give us 48 right there. And then on this side, we have 22 degrees. And up at the top, we have y plus y, which is going to give you 2y. And what we're able to do now is say that we know that there are 180 degrees in a triangle. And our triangle is split between 48 degrees, 22 degrees, and 2y degrees. So if we try and solve this for y, we can get 180 is equal to 48 plus 22, which is going to give us 70. Whoops. It's going to give us 70 plus 2y. And if we subtract our 70 on each side, we have 110 equals 2y. And dividing by 2, we can get that y is 55 degrees. And so now we have also solved for y. And so we only have one variable left. And looking at our picture in here, z, we can see that it's on a segment length. X and Y were both in angles, but Z is a segment. And for segments, we're not going to use the 180 degrees, but we can look at Z, and we can think about all the things that we know about segments in triangles where we have the incenter. And one of the things that we know is each of the segments that takes you from the incenter to the side is congruent. So we have 7 on this one. We have another 7 down here. And we have our last 7 on this side. And what we're able to do now, we can look at the 7 and the Z, and we can notice that we have a right angle. So if we complete this as a triangle, we have the triangle contained of 7, Z, and 25. And I wrote that down here at the bottom so that we can see kind of what's going on in our picture. And when we know 2 sides in a right triangle, you'll have to excuse the cat. When we know 2 sides in a right triangle and we want the third side, we can use a squared plus b squared equals c squared, or the Pythagorean theorem, where we know that the side across from the hypotenuse every single time will have to be c. So we can plug in 7 and z and 25. And so 7 squared is going to give us 49. Z squared is going to stay z squared. And 25 squared will give us 625. Now when we subtract on each side, we get that z squared is equal to 576. Now when we take this square root, it turns out that 576 is a perfect square. And so we're able to say that z will be equal to 24. And so now we've gotten all of our missing pieces. We have filled in for x, y, and z, and we have completely finished the incenter.